Hello everyone, welcome to my YouTube channel Electronics Made Easy. The main idea behind this channel is to let you learn basics of electronics in a very easier manner. Today we will learn about logic gates. So logic gates, they are the basic building block of any digital circuit. In today's session, we will learn three basic gates that we have: AND, OR, NOT, and four derived gates derived out of these basic gates, that is NAND gate, NOR gate, exclusive OR gate, and exclusive NOR gate. So the first thing is that the input and output levels in any digital circuit, they are represented by high, that is logic 1, or a low, that is logic 0. So in logic gates, inputs and outputs, they can have only two values, either a high 1 or a low 0. So let's begin with the things and see first of all the Boolean expression, truth table, and the logic behind basic gates. So let's start with AND gate first. So AND gate, it implements the logic as AND means this and that, both the things. So that means in any AND gate, multiple inputs, if they have all high logic, then only the output is going to be high, otherwise output is low. So AND logic, let's repeat the thing. It is that if all the inputs are high, output is high. If any one input is low, output is low. So the symbol that we have for AND gate, it is being shown on screen. These are the inputs, and for this example, input blue colored, it has been represented as 0 logic, and the red color, it has been represented as 1. So if any one input is low, output is straight away low. Now, for every logic gate, we have ICs available in the market, and we can directly use them to implement the logic for that particular logic gate. So AND gate has IC 7408, which is a 14-pin IC, and it has quad. Quad means 4 AND gates can be realized out of this IC. Quad 2-input AND gate. Now next is the truth table. So truth table for any digital circuit, it is all the possible combinations of the inputs and what output you are going to get out of that possible combination. So if AND gate has two inputs A and B, so these four are the possible combinations that we can have, possible conditions that we can have for that inputs. So either both are low or both are high. So if both are low, that means both are low, straight away output is going to be low. If both are high, then AND gate, it is going to give a high logic at the output. And if any one is low, output is still going to be low. So this truth table of AND gate, it lets us define the Boolean expression of AND gate as that if both the inputs are high, output is high, and this is how the AND gate takes the Boolean expression as A dot B. That means if 1 dot 1, we are going to get out of the Boolean algebra, it has to be high. But if it is 1 dot 0, 0 dot 0, 0 dot 1, the expression will give us the value to be low. And one more thing, such an expression, it is termed as sum of product form, and to obtain sum of product form expression of any digital circuit out of the truth table, we see the combination of inputs at which the output is high. So for this, the output is high for this condition, that means A and B both are high. So that is why they have been termed as A dot B. So is this clear? Now next is how to obtain the logic of AND gate using diode, because every circuitry, definitely it has been framed using your active and passive elements, right? So how to frame AND gate logic, how the framing part of that IC has been done. It is, if we have these two diodes and we are giving high supply towards the P side and inputs have been connected on the N side. So let's see what happens. And definitely here we are obtaining the output across the P side. So if A and B both are high, let's say, so from here also it is going to be high, from here also it is going to be high. These are going to be not forward biased, not reverse biased. So that means they are in a non-conducting mode. So complete high voltage VCC, it is going to be obtained at Q and we are going to get output to be high. So let's take the case where if any one of input is low or both are low. So if A is low, B is high. So what will happen? A, which is on the N side of diode DA, will make this DA to be forward biased, and B, which is again high, so this is not conducting, while still diode DA is conducting. So VCC, it is going to be grounded through A, and Q will not obtain a higher value, and definitely it is going to give a logic 0. So this is how the logic of AND gate is formed. So AND gate, it can be also explained well with the help of switches in series. So as you can see the circuit, if both the switches are on, then only your bulb is going to glow. If any one switch is open, your bulb is not going to glow, and the same applies if both the switches are open. So next we have OR gate. OR gate is this or that, means the purpose is going to solve even if any one input is high. So if any one input is high, output is high. If both the inputs are low, only then output is low. So this is the symbol for the OR gate that you can use in your circuit diagrams. As depicted over here in the example, 0 and 1 at the inputs, it is going to give 1, that is a high logic at the output. So IC 7432 is a 14-pin quad 2-input OR gate IC. Truth table for OR gate, it applies that if both the inputs are low, output is low, while for other 3 possible combinations, output is high. And through this, you are going to obtain the Boolean expression as A plus B, Boolean OR. So it depicts as if 0 plus 0, it is 0. 0 plus 1, 1. 1 plus 0, 1. And 1 plus 1 is a definite 1. Next, let's see how functionality for the OR gate it has been derived. So here I have taken up 2 diodes. Inputs are given on the P side while ground has been connected on the N side, and output is also taken towards the N side. So if any one input is high, so definitely that particular diode, it is going to be in forward biasing, and that high logic level, it is going to be conducted to out, and definitely out is going to be high logic. While if both the inputs are low, the diodes, they will remain in non-conducting state and out will be a logic 0. So again, switches are a good way in which you can depict the logic of logic gates. So if switches are in parallel, don't you see that they define the OR gate logic? That is, if any one switch is open, okay, not any one, that is, if any one switch is closed, so it is going to make the circuit and the bulb is going to glow. Even if both are closed, still the circuit is made. But if both are open, the circuit is not made, it is broken now and the bulb is not going to glow. Next comes NOT gate. So NOT gate is a single input and single output gate, which is negation of input. So whatever logic you will have at input, it is going to have the reverse of that at the output. So a 0 at the input, it gives 1 at the output. Likewise, 1 at input gives 0 at output. And this is the symbol for the NOT gate that we use, IC 7404. It is hex inverter IC. That means it is hex. Hex means 6. So 6 inverters can be realized out of this 14-pin IC. So truth table, it has only 2 conditions of input, and output is the negation of input, and it has been depicted with the help of a bar over the input. So A bar, X bar, Y bar, this is the expression for the NOT gate. NOT gate, it can be realized by a transistor. So transistor in a common emitter amplifier configuration, it inverts the input and the output. So the same circuitry that has been followed up over here, and it is going to give us the inverted input at the output. Next, we come across derived gates. So derived gates are the ones which are formed by the combinations of basic gates. So first of all, let's see NAND gate. NAND gate, it is the negation of output formed by the AND gate. So it is opposite of AND. So AND says that if all the inputs are high, then output is high. So what will NAND do? If all the inputs are high, output is low. So this is the symbol for NAND gate, similar to AND gate but inverted, so that is why a circle after it. So Boolean expression, AND reverse, that means Boolean expression for AND with a bar. So A dot B whole bar, it represents the Boolean expression for a 2-input NAND gate, and the truth table also applies to if both are high, output is 0. For the rest of the 3 combinations, that is if any one is 0, output is high. Next comes NOR gate. Okay, we haven't done NAND gate IC, so 7400, it is a 14-pin quad 2-input NAND gate IC. Next is NOR gate. NOR gate is again reverse of OR. OR says if any one input is high, output is high. But what will NOR say? If any one input is high, output is low. So in this case, it is that let's see if our inputs 0 and 1 are here at the output, output is going to be 0. NOR gate IC 7402, it is a 14-pin quad 2-input NOR gate IC. Boolean expression, whatever it was for OR, it is the bar of that, it is the complement of that. That is A plus B whole bar. And the truth table, it reveals that if any one input is high, output is low. If both the inputs are low, output is high. Next, a very important IC, exclusive OR gate. Exclusive OR gate, it states the logic in the form of equality or inequality. It will check whether the ICs, whether the inputs, they are same or they are different. So exclusive OR gate, it is going to give us a logic 1 at the output if both the inputs are different. If inputs are different, let's see here in the example 0 and 1, output is 1. But if inputs are same, it is going to give 0 logic. And this is the symbol for exclusive OR gate. Exclusive OR gate, it is often denoted by this symbol, that means a plus sign in a circle. So the truth table, it reveals that if both the inputs are same, either 0 0 or 1 1, output is 0, while if inputs are different, output is 1. Exclusive OR gate, it is framed as a combination of AND gate, OR gate and NOT gate, and this is the sum of product expression for the exclusive OR gate. It can be obtained from the truth table itself. Let's see the case. To obtain the SOP, that is sum of product form for exclusive OR gate, we need to see when both the outputs are high. Output is high when X is 0, Y is 1